Displacement current, Maxwell's correction. Physics for everyone welcomes you. Here we are going to learn about Ampere's circuit law, Gauss law. Next, charging a parallel plate capacitor. With the help of this small activity, we will be learning Ampere's circuit law, in that what is the correction made by Maxwell's. Ampere's circuit law, a current carrying conductor around which there is an Amperian loop. Good. Ampere's circuit law states that the line integral of magnetic field over a closed loop is mu naught times net current enclosed by the loop. Ampere's circuit law states that the line integral of magnetic field over a closed loop is mu naught times net current enclosed by the loop. Mathematically, integration closed loop B vector dot dl vector equals mu naught time I enclosed. Let us read the Gauss law. Plus Q is the stationary charge. Let us imagine a surface enclosed this charge. Gauss's law states that if a charge Q is enclosed by an arbitrary closed surface, then the total electric flux phi E through the closed surface is phi E equals integration closed surface E vector dot dA vector equals Q enclosed divided by epsilon naught. Good. Gauss's law states that if a charge Q is enclosed by an arbitrary closed surface, then the total electric flux phi E through the closed surface is phi E equals integration closed surface E vector dot dA vector equals Q enclosed by epsilon naught. Charging a parallel plate capacitor. Here we are charging a parallel plate capacitor. Let a time dependent current IC called conduction current be passed through the wire to charge the capacitor. There is a magnetic field around the current carrying conductor, so using Ampere's circuit law for the loop L1. Here we have an Amperian loop L1. When you keep a magnetic needle close to this loop, we will be finding the magnetic needle gets deflected. Thereby we confirm that there is a magnetic field around the current carrying conductor. We are applying this Ampere's law here. Integration closed loop L1 B vector dot dl vector equals mu naught times the conduction current IC. Integration closed loop B vector dot dl vector equals mu naught times IC. Good. There is a magnetic field between the plates of a capacitor. So, using Ampere's circuit law for the loop L2, when we keep a magnetic needle between the plates of a parallel plate capacitor, the magnetic needle deflects. Thereby we confirm that there is a magnetic field between the two plates of the capacitor, and we are applying Ampere's circuit law for the loop L2. Good. Integration closed loop L2 B vector dot dl vector equals mu naught times, there is no net current, conduction current between the plate, no flowing of charge, so mu naught times 0. So the right hand side of the circuit law becomes 0. Integration closed loop L2 B vector dot dl vector equals mu naught times 0 equals 0. Good. When applying Ampere's law to a closed loop, both the integration should give the same value. But here the two integrations are giving different value. So there is a mistake. There is a correction should be made. That correction is done by Maxwell's. Maxwell's resolved this inconsistency. Maxwell's correction or Maxwell's solution. There must be a current associated with the time varying electric field, time varying electric flux between the capacitor plate. There must be a current associated with the time varying electric field between the capacitor's plate. This is known as displacement current flowing between the plates of the capacitor, and it is given by an expression ID equals epsilon naught d phi E by dt. This equation can be found with the help of Gauss's law of electrostatics. Gauss's law statement, not statement, the formula. Phi E equals Q by epsilon naught. Differentiating d phi E equals dt equals 1 by epsilon naught dq by dt. dq by dt equals epsilon naught times d phi E by dt. Good. This epsilon naught d phi E by dt is called the displacement current ID. dq by dt equals ID is known as displacement current. Here the dq by dt is not rate of flow of charge, but it is rate of charging or rate of discharging. This rate of charging or rate of discharging in the plates of the capacitor is called the displacement current. On the right hand side, epsilon naught d phi E by dt, we name it as the displacement current ID. This has to be substituted in the second integration. So the second integration becomes integration closed loop L to B vector dot dl vector equals mu naught times ID. Now we have to add these two integration to get our problem to be solved. Maxwell's modified Ampere's law as integration closed loop B vector dot dl vector equals mu naught times the I. The I may be either conduction current or the displacement current. Mu naught times IC plus ID. When IC is present, ID is absent. When ID is present, IC is absent. Integration closed loop B vector dot dl vector equals mu naught times IC plus mu naught times epsilon naught times d phi E by dt. This is Maxwell's modified Ampere's law. When the current in the circuit is constant, the displacement current becomes zero. For the loop L1, let us look at for the loop L1, here you have the conduction current IC but no displacement current, right? In this loop, you don't find any d phi E by dt. So you don't have the second term for the first loop. Integration loop 1 B vector dot dl vector equals mu naught times IC. Let us go for the second loop. In the second loop, we don't have the first term mu naught IC. There is no conduction current between the two plates of the capacitor. Between the two plates of the capacitor, there is a change in magnetic field. That time varying change in magnetic field is responsible for the current conduction. This current conduction is called displacement current. So integration closed loop L2 B vector dot dl vector equals mu naught times IC. ID equals mu naught times epsilon naught times d phi E by dt. Now let us learn little bit more about the loop L2. The conduction current is zero in an empty space, but the displacement current does exist. The electromagnetic wave propagate. When electromagnetic wave propagate, there is a change in electric field that is the cause for the production of change in magnetic field. The change in magnetic field in turn produces the change in electric field, right? So the change in electric field is nothing but the displacement current. So the electromagnetic wave propagation, you have the displacement current, but not the conduction current where there is no charges available there. The name stuck because Maxwell's named it. The word displacement is poorly chosen because nothing is being displaced here. Thank you, children.